Today I'm going to talk about meta-analysis, and when I was thinking about how do I attack this presentation, it's sort of a really big topic. There's a lot of things to sort of talk about with meta-analysis. There's my colleague Mark Goodrich, who's also in the Special Ed Communication Disorders Department, and I just taught a course on this, so we've taught a whole semester on meta-analysis. And it takes a long time to do a meta-analysis, so it's hard to sort of condense everything into a single presentation. So what I'm going to try to do is give an overview of what meta-analysis is, but then I'm going to try to talk about some different methodologies that you can use, really sort of more recent methodologies in meta-analysis, and how those methods can help you answer particular questions. One of the things that I sort of was thinking about as I was planning this was that, sometimes we get stuck in the details of an individual study or individual studies. And as we're trying to look at these individual studies, we sometimes lose sight of the big picture. So I, titled my, presentation, Seeing the Forest Plot for the Trees. Here we are, we've got our, forest plot on the right-hand side, and as you can see, you can't see anything. There's trees everywhere. So we got to get rid of those trees if we want to really be able to see the big picture here. For some reason, this is not. Oh, there we go. Trees are gone. Thank goodness. All right, and this is what a traditional forest plot might look like for meta-analysis. As you can see, there's some studies on the left-hand side, with effect sizes. Those effect sizes, are for particular measures. And on the right-hand side, there are, the G statistic, which is the effect size, confidence interval around that effect size. And then in the center, you've got the plot where you see all of the effect sizes plotted with their confidence intervals around them. And then, the line sort of that's here down the center is the average weighted effect size. And I'll get into what I mean by weighted effect size afterwards. And you can see this particular average weighted effect size was negative 0.97 with the confidence interval of negative 1.09 and negative 0.86. So it's pretty significant negative effect here. And the forest plot just sort of allows us to see how varied the effects are around that effect size, from all these different studies. So you can see how it gives us a little bit of a bigger picture. All right. To give you a little bit of an overview of what I'm going to talk about today is, I'm going to start with just the need for meta-analysis, which I've already started to do a little bit. Prior meta-analytic technique, and limitations of that technique, and so why this presentation now. New meta-analytic methods that have evolved in recent years that you can sort of think about if you're planning to do a meta-analysis. How those new methods, expand the potential research questions we can ask, and how they impact the steps that we go about using to conduct our meta-analysis. I'll provide some examples of studies, one in particular, but probably a variety of different examples, and then an introduction to meta-SEM, structural equation model, meta-structural equation modeling, which is sort of a new thing. And I won't go into examples about that. It's sort of new to me as well, but I'll provide sort of an overview of what that can do for us. So the need for meta-analysis is pretty great. So, sometimes when we're looking at individual studies, there can be a lot of things that can go wrong. There's issues with, maybe sometimes small sample sizes, some flaws or some biases that can go into, a single, study. And, over on the right-hand side of the screen here, you can see sort of a picture of the cold fusion experiment, right? So where, somebody's trying to replicate the cold fusion study. And sometimes, we just may have problems with a particular study. And so we need to look at, additional studies, right? We need to replicate in order to really be confident about our results. So replication is necessary. However, there's some issues around replication, right? So, copy of a copy isn't quite the same as the original, right? So I don't know if you guys have had old cassette tapes that you would try to, like, you had a blank that you copied something on and tried to copy it onto something else. It was never quite the same, right? And so, replications when in research often involve changes. Researchers don't tend to like to just do a straight replication. And even if they did, they would have a different participant sample, likely. They may have a slightly different setting or different dosage or length of treatment, or they may add a different wrinkle to the experiment. And so replication is necessary, but there are some of these considerations to think about with replication. And even when you have replication, it's sort of difficult to summarize a large literature, right? So we may have like a lot of different studies. This is an example of a table that I used for a meta-analysis where I was really trying to like summarize all of the different features of what's going on. And this is in a table form, and it's still very difficult to sort of to follow. How many studies used signal words in their instruction? How many studies involve some kind of writing? So and we've all read these really long literature reviews and even written them, in dissertations and things like that, where we're sort of trying to summarize the literature, and it can be very overwhelming, especially when it's a very large literature. So that's one issue. And another thing is that there may be some conflicting results across studies, right? And so just to sort of make this, relevant to today, and coronavirus and all that. So there's been a lot of news around different potential drugs that might be helpful for patients that have coronavirus. Now, I haven't read these studies, but there are some news articles about the studies, and so I apologize. Again, if we're doing a meta-analysis, we wouldn't be using news articles. But, we see in a headline here that there's a new drug that there's positive results, but they're inconclusive. There wasn't a control group randomly selected to receive a placebo, and so therefore it's difficult to determine what the results mean. There's another study that came out that showed no benefit for coronavirus patients. The company still saw reasons for hope. Many ongoing trials don't have a placebo and may be unethical to withhold treatment. So there's people that are arguing for that. There's a frenzy of research we're hearing, so there's a lot of different studies maybe going on at the same time. And there's conflicting information in these studies. But then, more recently, there's been some hope. There's been a really big study that's shown that there is some promise for this drug. And so, what do we believe, especially when we have these conflicting results? Do we believe the studies that didn't find the results, or do we believe the studies that did? And then, if we have a single study, we all know that we need to do replication. So what can we do? So meta-analysis is sort of a thing that we can do that can help us sort of make sense of all of these different studies. And what the approach is it allows us to statistically combine quantitative research findings. So studies that have looked at groups of individuals and compared them, or compared treatment group with a control group in a quantitative way, or studies that we can examine with a meta-analysis. The results of a meta-analysis are an average weighted effect size. And that is usually, it's essentially in terms of standard deviation units. And so if you can see that the normal curve on the right, I've got two normal curves, one for a treatment group, one for a control group, and the effect size is 0.73. And so essentially what that means is if a student was at the 50th percentile and they received this intervention and realized this effect, they would then be at the 77th percentile of the control group. So that just gives you a sense of how it gives us a magnitude and a direction that allows us to sort of see whether or not there was a difference made, with this treatment. These meta-analysis may provide more precise estimate than an individual study. I would say on par, that's true. There may be an occasional individual study that nails it and it's got the very very close estimate of the actual true effect. But we don't know that, and so a meta-analysis can provide a better, more precise estimate for us in a lot of cases. I want to before I go on, I want to talk a little bit about there were two other presentations that were sort of done by the Map Academy and part of this video series. One was done in 2011 by Elizabeth Mormon Kim, and another in 2015 from Amy Dent. And so they both, I watched these presentations. They were very nice presentations. And so the question is, well, why am I doing another one? Why do we need another presentation? And I think the reason for it, and as I was thinking about it, is there's been a lot of changes to meta-analysis, as I alluded to earlier, in the last 10 years, and really a lot of those methodologies methods have really started to catch on in the last 5 years or so. But these presentations were great. They showed really a lot about how to conduct a literature review, how to code, inclusion/exclusion criteria for studies, how to integrate the findings or do data analysis, right? So they had these big topics in meta-analysis, and a lot of these haven't changed. So a lot of these things are pretty similar. The way that you conduct a literature review is, doesn't change because of the methods that we've that I'm going to talk about today, anyway. So I probably won't spend a lot of time on those things, and I'll refer you to those presentations instead. As I mentioned, have been some important advances in the last 5 years, and there are three here that I've listed. I'm going to really, talk about primarily number one, methods for including more than one effect size per study. This has been a limitation of meta-analyses. It was a limitation for many years, I'll talk about what that means, and why we can only include one effect size per study. And there are these new methods, robust variance estimation and multi-level modeling, things that have, some researchers and statisticians and methodologists have developed these solutions for us that we can now include more than one effect size per study. And I'll talk about why that's important. And then, meta, structural equation modeling. I'll talk a little bit about what that can do for us. There have also been some advances in single case design effect sizes. And I'm not sure how familiar you all are with single case design research. It often means that we have 3, 4, 5 participants in a study, and each of them is in a baseline condition, and then they have an intervention condition, and you're looking for an effect across the baseline intervention. And so it's controlled very differently than an experiment, a randomized control trial, or quasi-experiment even. But there are some advances where we can maybe get some effect sizes for individual students. They're not quite comparable to effect sizes in group design research. And so it's not something that we can necessarily combine with group design meta-analyses. But I think there have been some nice advances. And so, I sort of invite you to go look at the literature if you're really interested in single case design. I think that there's some good ways to do meta-analysis with single case design these days, but I probably won't spend a lot of time or any more time on that unless people have questions later. I'm going to primarily focus on robust variance estimation. I will talk a little bit about multi-level modeling as well. So here's a traditional meta-analysis. I just want to share, this one has a number of studies on the left-hand side. You can see the study names listed there. The next column over, you can see the Hedges G effect size with the standard error and variance, and then lower and upper limits of confidence intervals. And then on the right-hand side, you can see the forest plot. And the forest plot, again, allows us to see the variation around that average weighted effect size and really kind of see the heterogeneity that exists among these studies. And so you can see there's quite a bit of heterogeneity around them. One of the things I wanted to point out is here on the I'm not sure if you can see my arrow or not, but I'm kind of going around these study names. If you look down the study name list, every study shows up one time. There may be an author that has more than one paper, like Alverman 1981 and Alverman 1982, and those are different studies. But each study has only a single effect size represented. But we know that is sort of not always, let's see, there's something on my screen that I didn't anticipate being there. But anyway, we know that there's some studies, there are a lot of studies that have multiple outcomes, right? So it's sort of unrealistic to say there's only a single outcome with the study. Often we've got studies, so I'm going to give you an example of an impacts of in an intervention on reading comprehension. So imagine we're doing a study and we want to know what the impacts of this intervention are on reading comprehension. Students will read, afterwards they get to the post-test and they read something, and then they complete a multiple choice test. And they also complete an oral retell, or also complete a written summary of what they've read. Or they answer short answer questions in addition to the multiple choice test. Or they generate their own questions. There's a variety of things that the tests that these students could be taking. And so the question is, if we have to only use a single effect size, what could we do, right? And so people, what they would have to do at in this old approach was they would have to maybe choose a particular test, and they might say, oh, the multiple choice test is the most representative of reading comprehension. So we're going to use that test. But that's debatable, right? Other people might argue and say, well, the multiple choice test really isn't the most representative of comprehension. Another thing that we could do, and people had done, was average the effects across these tests within a study and get a single effect size, right? Now, could be problematic, again, because there's some dependencies in there, but it is something that a solution that people did. Another thing that we could do is we could randomly select one of these as the representation of the effect on reading comprehension. But you can see that none of these are really satisfying in terms of what we could potentially do. So I think that's one of the issues. Another issue here is, what about studies with multiple subgroups? We know that sometimes researchers are interested in comparing interventions, and how intervention might work, say, with students with disabilities or students without disabilities. And sometimes, I don't know if you've come across this, but I certainly have. Sometimes the researchers don't combine the groups and give you an overall analysis. Instead, they give you the analysis for students with disabilities and then analysis for students without disabilities. And so, I guess, what could we do in that situation? Could we choose one group, or could we somehow combine those groups? And I'll talk about that in a second. Actually, I'll talk about it now. Just go on to that. So one of the questions is, could we average the effect across these two groups? And we could, and it's possible to do this. We just have to kind of account for there's different group sizes here, so we need to make sure that the average is weighted for these groups. We also need to kind of think about, but if we do that, then maybe we're sort of weighting this effect size more for the kids without disabilities. We also have to kind of think about the within group variance here and between group variance as well, because sometimes if we just average these things and we miss having that we miss out on the between group variance, and that can be problematic. We're not really getting a good representation of what the actual effects are. In study 2, here's an example. We've got maybe some people are interested in doing a research study, and they want to just examine the effect of an intervention for different grade levels. And they don't want to group these grade levels together because they think they're very different from one another. And so they give us the effects for each grade individually, right? And so the question there is, could we average those? And again, certainly we could. We have some of the same issues. Another option would be to choose one to examine. If we did that, could we do it? Sure, we could, maybe we could do that, but it really depends on our inclusion criteria. Are we interested mostly in first grade students? Are we interested in outcomes for the third grade students? It really depends on what we're sort of looking for. One drawback to selecting a single grade level here is that we would lose a potential moderator variable. We wouldn't be able to analyze potential differences between the grade levels anymore. And so that's sort of an issue. So then you might ask, well, why couldn't we just include multiple effect sizes within a single study? And so, maybe alluded to this a little bit. One reason is that there are statistical dependencies, among these effect sizes. The effect sizes from the same study include the same participant sample, researcher, intervention components, and so a lot of things are done the same way, and so those effects are going to be correlated with one another, and so that's a little bit problematic. The other thing is that there's weighting involved in meta-analysis. So what we tend to do is we give statistical weights to each study based on their variance, which is really related to their sample size. What that means is we trust larger studies more than we trust small studies or small samples, right? If we're doing a random sample of the population and we have a really small sample, it could be representative, but if we only have a few participants from that sample, then it could be that they're really not representative. Maybe even if we're randomly selecting, it could be that we randomly select from a tail of the distribution, for example. We feel like as you sample with larger sample, as you have larger samples, you get closer and closer to the true sample, and so samples with larger or studies with larger samples are going to get more weight. That's an issue. And then the other thing here is that, so because of that, the other thing with the weighting is if we have multiple effect sizes per, for a particular study, we've got one study that's got, a smallish effect, and that, we've got that study, it's already not getting a lot of weight in the analysis. And then we have another study that's a little bit bigger, and we've got maybe 2 outcomes or 3 outcomes. And every time we add an outcome, we're adding more weight to that effect size, which biases the results toward that particular study, just because it had more measures. And so that was sort of problematic. So what people have done is they've some researchers and methodologists, statisticians have developed some approaches to robust variance estimation and multi-level meta-analysis that now both allow for inclusion of more than one effect size from a study. And so that's where I'm going to talk about a little bit is how do we how does this help us, and what do these methods do for us? So the first one is robust variance estimation. Essentially, what robust variance estimation does is it looks at the residuals of the effect sizes, within the sampling variance of the meta-analysis, and it uses that to sort of estimate what the covariance structure is of the group of effect sizes. And so by doing that, it allows it statistically sort of, increases the standard error around the effect, and it makes it robust to, it sort of really increases the confidence interval and makes the effect robust. It's nice because it can be used with as few as 10 studies. And we don't have to know what the actual covariance structure is of the we don't have to know what the actual covariance structure is of the effect sizes. We don't have to know what the distributional assumptions are. It's very easy to implement this, and this last bullet point's really sort of a really great thing is that we don't even need to know what the source of the dependencies are. And I will talk about some different types of dependencies, but robust variance estimation sort of doesn't, it's great if you know the source of dependencies, but often there are multiple sources of dependencies, and this method is robust to that. The multi-level modeling approach, on the other hand, is sort of, if you are familiar with HLM or multi-level modeling in general with regression, then you know that often we may be thinking, especially if we're doing school-based research, we might be thinking about children nested within classrooms that are nested within schools, and we can control for the variance that's at the different levels, right? We can control for that clustering. Well, we can do the same thing with meta-analysis, it turns out. We can have participants clustered within outcomes, and those outcomes clustered within studies. And so we can do a 3-level model. Now, if there are multiple outcomes, this doesn't necessarily, you would think that it wouldn't hold because the participants would be clustered under one outcome, and then they'd also be clustered, the same participants would be clustered in another outcome. And so then that doesn't exactly work. But, as it turns out, we can still use this this method anyway. It doesn't really model the variance at that participant level, so it allows us to still get pretty robust, findings from this. There are some advantages to this. Some advantages are that it allows for additional levels of nesting. We can have studies nested within a research lab, or studies nested within a country, if we want to sort of examine whether there's some variance at that level. We again don't need to know the sampling covariance for individual effect sizes, and it allows the researcher to examine moderators that affect outcomes differently. So we can sort of look at different outcomes, and so it allows us to sort of look at within and between level variance, between study and within study variance. However, there's been a study that's by Moyart et al. And what they found in some Monte Carlo simulations was that this is really not a very reliable estimator if we don't have that many studies. And so they recommend using this only if there are at least 50 studies or more. And so that's a little bit of a drawback. All right. So I'm going to show you, this is the same forest plot, or at least it involves the same studies that I showed you previously. Right. So in the previous forest plot, you saw that there was a single effect for each study. And now you can see that we've got studies listed here on the left-hand side. And the study has, a couple of effect sizes that are associated with it. And those, there are effect size IDs below each study. And you can still see, and you can see the effect sizes represented with the confidence interval around those effect sizes. And you can see the effect sizes on the right-hand side. If you see a study that's got, or an effect size that's a little bit larger than others, and typically what that means is that brings a little bit more weight into the meta-analysis. In this case, because we have, for Bakken et al., for example, there are 6 effect sizes there. Essentially, the weight of that study gets divided among those six effect sizes. So that's why you see a lot smaller influence of each of those independent or individual effect sizes. So I mentioned before that robust variance estimation doesn't matter what the dependencies are among the effect sizes, and I just want to talk a little bit about what that means. So here, if we're looking at that Bakken study again, we see those 6 effect sizes, and we, as I mentioned before, the same researcher, same participants, same methods being used, and so this is the correlated effect size. This is a correlated dependencies sort of issue, right? So within this study, these effect sizes are going to be correlated with one another in some way, likely. On the other hand, we look at Bartlett down here. Bartlett et al. We've got an effect size for Bartlett et al. In 1978, one effect size, and then 1980, another effect size. And there's only one effect size for each one of those studies, so it's not problematic from the old, method point of view. However, as you can see, it is still the same research team, right? And so this would be more like the hierarchical dependencies case, where you may not have the same sample, may not have the same, may have sort of a different method or different context, but because you're because you're working with the same researchers, there may be some dependency. So these effects might be nested within this research lab. And so that's the hierarchical case, right? Then we see, like up here, we've got, Alverman, 1981, 1982, and then Alverman and Boothly, 1984. Each of those have 2 effect sizes. So within each of those studies, we've got correlated effects, but then we also have, this same author, same researcher doing multiple studies, and so we've got a hierarchical, dependencies issue, right? And it's okay when we're using robust variance estimation. It will allow for all of those things. It will give us a good estimate of the average weighted effect, even with those dependencies in place. All right. So, I just wanted to give you, for this study, I showed you that I had sort of a traditional meta-analytic approach already that I had done, and the effect size on that is like 0.58, right? With a confidence interval of 0.43 to 0.73. For a robust variance estimation, you can see that the effect size really didn't change that much. It's 0.57, with a slightly larger confidence interval, though, right? So now we think the true effect could be within a slightly larger range, and that's important. And even especially when we're sort of thinking about statistical significance, this one's not close to zero, so we're not as worried about that. But in some cases, if we were estimating something with traditional meta-analysis, we might think that we have a significant finding when actually we don't, right? It's sort of an artifact of these dependencies. In metaphor, this is the multi-level approach, and I'll talk about what metaphor is in a minute. It's in our package. You can see that the effect size is even different here. Now we have 40 studies, so I've got k equals 40 and n equals 170. So I don't quite have 50 studies. And so, the effect size is slightly lower. This could be, it could be that it's sort of lower because I don't quite have enough studies to really estimate with this estimator. Or it could be that, it's just that there's some differences in the way the effect is being estimated. So there's quite a few effect sizes in this, so it might be that. But again, all of these sort of, as far as the point estimate goes here, 0.54 to 0.78, I'm sorry, 0.54 to 0.58 is really not that large a difference in the effect. And so we're finding about the same effect, but you can see again, the confidence intervals are slightly different. I want to give you another example. So here's an example of this is a paper that I wasn't originally an author on, and it was another person who was working on this and then invited me to be an author on it later. They first tried to do the meta-analysis with a traditional meta-analytic approach with one effect size per study. And so that's on the top half. And you can see that there are several variables here. So writing quality, output, grammar, vocabulary, spelling. Each one of those is a separate meta-analysis. So I just want to be clear that this isn't a single model. Each one of those is a different meta-analysis. And you can see the number of studies involved in each one of those, and then the effect sizes that are associated with it, confidence interval, and so on. And then what happened was the reviewers for this paper said, we really need to update the approach and go with robust variance estimation on this. And so that's where I came in, got involved in this study. We changed the analysis to robust variance estimation analysis. And you can see now that I've got the same number of studies listed here. K represents number of studies, and then the N is the number of effect sizes that were in those studies related to those outcomes. See, there's a lot of grammar effect size and a lot of spelling outcomes. But if you sort of take a look here and compare the size of the effects, you can see that there's quite a difference in the effect now. I mean, it's still really only 0.04, but then there's quite a difference in the confidence interval as well. But then when we look at output, we see an even larger difference, right? And so here's where is the cautionary table. You might say, oh gosh, well the effects are pretty close, and that's not always the case, And so part of this is that as we're looking at these things, it may be that we dealt with outliers differently or had to deal with outliers differently when we were using the one effect size per study versus the robust variance estimation. There's a lot of different factors that come into play, but essentially we ended up with a very different effect size here. And so this could be kind of problematic. Just to give you a little background, this was comparison of students who have speech language impairments to their general education peers. The reason we see negative effect sizes here are basically because the students with speech language impairments are performing a lot lower than their general ed peers. And so this that's what this meta-analysis was aimed at showing, was what is the difference between them and their gen ed peers, and they're performing lower, and so that's why the effect is negative. All right, so I really started with the end there, right? Like I started with talking about what's the approach, and then here's what the results look like, and but I want to kind of return back to the stages of meta-analysis and the different steps that we tend to take, because these analyses, or going with these kinds of approaches, may impact a lot of these different stages. Really not, I say all stages here, but it's a lot of the stages, not quite all of them. And I wanted to point out too that, really a lot of times when people are doing meta-analysis, they're like, oh, this is pretty easy. But really there's a lot of work that goes into collecting studies, doing the literature search, coding the studies, contacting authors, extracting effect sizes. That's where 95% of the work happens with meta-analysis. So if you really want to do one of these things, be prepared to spend the time doing this literature review. It's going to pay off. The calculating the average weighted effect and doing moderator analyses, things like that, are really quick. That's something that a lot of analysts can do. But if you really want to have a great meta-analysis, you've got to spend the time on the front end doing a lot of the coding and the searching. I said that these things can affect the types of questions that we ask, and they do and they don't in some ways. So the first couple of questions here, the intervention question, comparing groups question, relation between constructs question, these are questions that we could have asked previously. So the types of questions that we might ask here are like, is the treatment effective? And for those types of meta-analyses, what we're going to be doing is comparing treatment groups to control groups, in experimental studies or quasi-experimental studies. My recommendation is always with quasi-experimental studies that you have to have a pretest that you can control for, because there may be pretest differences between the groups just based on the fact that it's a quasi-experiment, and you really need to control for those. Otherwise, you're biasing your analysis. We can also do a meta-analysis where we're comparing groups. Sorry, I'm just gonna, Seth, can you tell me what never mind, I'm just gonna look at my phone here. Just wanted to see how I'm doing on time. So sorry about that. We can also compare groups, which is the example that I showed you a few minutes ago, where we were comparing students with speech language impairments to their general ed peers, kids without speech language impairments, essentially. So we can also look at like students with LD versus students without LD, and LD is stands for learning disabilities. These studies don't have to be experimental in order to make these comparisons. They just have to have a separate descriptive statistics for the for both groups, so that you can calculate an effect size to compare those two groups. A third question that we can ask is whether there's a relation between constructs, and essentially we can look at correlations as an effect size. So if we want to know what the correlation is between, say, self-efficacy and math achievement, then we could find studies that have correlations, and then we can average those correlations using meta-analysis. It doesn't have to be the primary research question of study. So it could be that we look at an experiment and it happens to have a correlation that we're interested in. We can still use that study even though it wasn't the primary research question for that study. There is a need to transform correlations to Fisher's Z and back, and so I'm not going to spend really any more time on this because I just don't have enough time to do all of that. But I want you to be cognizant of, if you decide that you're interested in doing a correlation meta-analysis, that you'll have to sort of figure out how to do some of these things, and I'm happy to be a resource for you if you want to email me, or if you want to email Mark Goodrich. I'm sure he would be interested in, or he'd be able to help as well. I'm throwing him out there. And I think he's on this. He's watching the presentation, so I hope that he's enjoying that he's getting thrown in there. All right, but what this does allow for us to do, the types of research question that's slightly different now, is we always could have had a moderator analysis, but now we can sort of look at whether there are within or between study moderators that impact the average weighted effect size. And so essentially what we're trying to do is figure out, does the effect vary based on a particular, on a different variable, right? And so before, when we only had one effect size per study, we really couldn't look at within study variance there. We couldn't look at within study moderators. And now with robust variance estimation, we have that capability. So, what does that moderator look like? Well, we might want to say we're looking at like sort of the effect of drinking on productivity, right? For many people, if they're drinking a lot, then maybe their productivity goes down. Or maybe, as they get older, they build their tolerance up, and then they can handle a few drinks and then still be really productive. Or it could be that maybe when you're younger, you bounce back from drinking a little bit faster, and so then you're more productive. I don't know how true any of these things are, but it's kind of a fun example. And so age might be something that we would say, does age moderate the effect between drinking and productivity, right? And so that might be a way that we would ask that moderator question. I'll talk more about moderators in a little bit, but the other things that I sort of want to talk about, and this is just sort of an aside. This is not related to really RVE as much, but I do want to mention that it's really important to do a strong literature search. It really should be comprehensive. I think a lot of people will end up not getting dissertations or not searching out dissertations in their lit search. And that can be problematic for a variety of reasons. The primary one being that many times we hear people talk about publication bias in the fields, or in all of our fields, right? Where studies that don't find effects are studies that don't get published, right? And so if we're doing a meta-analysis and we're only looking at studies that are published, and if that publication bias is real, then we're going to have an inflated sense of what the effect size is. We're going to say, oh, this really works great, when really there are a lot of studies maybe potentially dissertations that couldn't get published, or other conference presentations that couldn't get published that show that there was no effect, or maybe that average effect is a lot smaller than we might really think it is by just looking at the published research. So we want to look at dissertations. You want to also do ancestral searches. So you want to, as you collect studies that meet your inclusion and exclusion criteria, you want to look through the reference lists and see if they reference any other studies that are similar, that they may be replicating. And you also want to do, I don't know if people are familiar with this, I think most people are, but if you go to Google Scholar, I don't recommend using Google Scholar for your primary literature search, but for forward searches, it's really useful if you put in the title of a paper, and it will find that paper for you. It will tell you how many times it's been cited. And if you click on that cited by, then it will bring you to all of the papers in Google Scholar that it's found that have cited that paper. And so you can do a forward search to see if anybody else has cited that paper and maybe is doing similar types of research, and that you could find additional studies that way. Hand searches of journals are great. You should pick a journal or two that you think that you find a lot of studies in, or that are publishing a lot on this, and do a search of the table of contents for all of those, for every volume that you can, for a number of years, to see if you can find relevant papers. You also want to try to contact authors, and you might contact authors in a couple of ways. One, you might contact authors if you see that somebody's published 4 or 5 studies that are getting included in your meta-analysis. It may be that they have 1 or 2 more that either haven't been published yet, or that are they didn't find effects, or they had difficulty publishing, and so they end up being sort of file drawer studies. And so you want to contact authors in those instances. Another instance is if you can't calculate an effect size, you may want to contact an author to get more information about the study. coding, as you code studies, so as you collect studies for your meta-analysis, we have to start coding them. We code them for a lot of different kind of features. Some of them are listed here on this page. So the study sample and context, study design characteristics, study quality measures, and effect size data. Right? So these are the things that we're going to be looking for. But it's important because RVE sort of changes the way that we code studies. So here's the way that you're going to need to set up your coding sheet when you're coding these studies. Typically, when we had a single effect size per study, we would have a study that, like, say, number 2, Abu Rabia 2004, and we would just use a single row for that entire study, right? And so we wouldn't change anything about that row, or we wouldn't have any additional rows for that study because there would only be one effect. However, with robust variance estimation, we have multiple effects, or for multi-level modeling, we have multiple effects that we can include. And so you can see for Abu Rabia 2004, there are actually 3 lines that we're using, or 3 rows. They all have the same study identification number, but they have 3 different effect size identification numbers. And that will become important when we run our analysis. You can see the effect sizes for each of those 3 outcomes, standard error, VAR. I always label my variance VAR just because that's the way I code, or when I write my syntax in the stats programs. So I always try to keep my variables named the same way. And you can see that I've got some other codes here. So the average chronological age of the student, the average the centered chronological age of the student. So basically the earliest age was 5, and so I subtracted 5 from every the chronological age of every student, so I would have an interpretable intercept. You can see that sort of I had some things that are coded yes or no, and then for the purposes of doing my analysis, I had to dummy code those so that I would be able to run the analysis, because the stats program will read it better as a number. So this is how you would basically set up your code book. This is the way that this is sort of, I sometimes will have a code book, and then I have sort of my clean data sheet that I use for my analyses. This is my cleaner data sheet. You can see this is sort of an earlier version because there's a couple of things missing. But essentially, it's the coding is the same as you do the coding in the same way with multiple rows. There are lots of ways to extract effect sizes. There's lots of different effect sizes that you can extract from a study, and there's lots of ways to extract an effect size from a study. Good meta-analyst will be able to find ways to get an effect size from a study that you might not have expected, right? So there are all these different ways. Some people might just say, oh, they don't have means and standard deviations, so then I can't calculate the effect size. Well, not so fast. We can look at gain scores and gain score standard deviations, or regression coefficients, 2A ANOVAs, means and ANCOVAs, things like that. You can contact the authors for more information. There have been times where I've seen people, and I've actually sort of worked with students who've been able to extract effect sizes from graphs because they were able to find the mean, and then they were able to find they had another test maybe somewhere else, or in ANOVA where they could get to the variance that they needed. And so there are lots of different ways to extract effect sizes. As an example, what I've done is I've put a resource in here for you for the Campbell collaboration calculators. This is a website. Campbell collaboration is very trustworthy in terms of meta-analysis. You can see that on the left-hand side here, there's a standardized mean difference. If you click the plus sign, what you do is you get a menu of all of these different effect size estimators that you can use. It doesn't cover every type of estimator or every type of way that you can get an effect size, but there are a lot of them in here, and it's just a really good resource. On the right-hand side, you can see if you are looking for correlations, sometimes you might just say, oh, it doesn't have a correlation, so I can't use that. But you can use means and standard deviations, and you can then convert those. You can use that and convert it into a correlation, or 2x2 frequency tables you can convert into correlations. And so so this just gives you a sense that don't stop as soon as you say, well, look at the statistics and then you don't find exactly what you're looking for. There may be some ways to get that effect size out for that study. And that's important because, again, if you lose studies, then you are sort of, as you lose studies from your analysis, you're sort of not able to really get the best estimate of what that effect size is. There may be need to convert effect sizes sometimes. Sometimes studies will report something like, oh, the effect size is partial eta squared. And you can actually convert that. There are formulas where you can convert that to an F into a D statistic if you are using Cohen's D as your effect size. You may need to convert, as I mentioned before, if you have quasi-experiments and they needed to include pretests, then you need to sort of control for pretest differences. You do that on all quasi-experiments. And so there you might subtract the pretest scores out from the post-test and then divide by the pool of standard deviation to get your effect size. Small sample bias. This is something that I use to basically Cohen's D is upwardly biased in small samples, and so in order to do that, there's a small sample correction. If you apply this to every effect size, basically as the n gets larger, that increases the denominator, and then basically the small sample correction sort of goes away. And so if you apply this to every study, then it's not going to hurt the larger studies at all. Also, you want to think about clustering. If you've got a cluster randomized trial, then there's variance associated with the classroom that, and if they analyze at the student level, then we really have to kind of control for that. And so we can adjust the effect size. And I don't have the form, it looks like I forgot to put the formula in here, but I can, if you want to email me, I can talk with you about that. Once we've got our effect sizes, what we want to do is examine for potential outliers, right? So we want to see if there are any sort of effects that really sort of seem out of the ordinary, that they're going to have a lot of leverage on our average weighted effect, and maybe give us a poor estimate of our average weighted effect. So the way to do this is to calculate the interquartile range of the effect sizes. You will then multiply the interquartile range by 2 or 3. I favor 3, and a lot of analysts do. It's a little bit more conservative. It allows you to it allows you to sort of keep the influence of that effect a little bit more. You add and subtract the value that you get from that IQR times 3 from the mean of the effect sizes. So then you get the outer fences. So you subtract the interquartile range times 3 from the effect, and then you also add it to the effect, and you get your sort of outer fences around that effect size. And then what you can do is analyze whether any effect sizes are outside of those outer fences. And if they are, then those are potentially outliers that you would want to deal with. And if so, you can deal with them in a couple of different ways. One, you could drop those effects. You could say these are overly influential and it's unrealistic that these are really this large of an effect, especially if it's something like an effect of like 5 or 6. Remember, we're talking about standard deviation units. So those really don't make a lot of sense. And so you could drop those effect sizes. Another thing you can do is analyze with and without those effect sizes in and see if it makes a difference in your average weighted effect. Or you could Winsorize the outliers. And what that means is you can change the value of those effect sizes to the value of the outer fences. So if it's like larger than the mean effect past the outer fence, you could pull it back to the outer fence by changing the value. And the advantage of that is you get to keep the information from that study within the analysis. It's still the largest effect in your analysis, so it still has some weight that it applies. But then you don't lose all of the information. So it's and it doesn't have such an undue influence potentially. The next thing that you need to do is sort of decide if you want to do a fixed effects or random effects model. I'm not going to spend a lot of time on this, except to say that most of the time we're going to be using fixed effects models. Random effects models. If you're using a fixed effects model, it's essentially because you think that you have like a really tight group of studies. This is the corpus of this, and that the actual population effect size will be within these effect sizes. And you can see that all of the effect sizes around this sort of like they capture that population effect size. Often we don't have this, and really we want to generalize to a larger set of studies, and so we use a random effects model that sort of rather than thinking that we have one population effect size, we have sort of a population of effect sizes, and there's a variety of effect sizes that we're pulling from this population of effects, and so the mean sort of is around this distribution of effect sizes. All right. Once you've done all of that and you've decided, how you want to, calculate your effects, then what you can do here is, then you'll calculate the average weighted effect size. You're ready to sort of run your analysis. And so for robust variance estimation, there are two sort of packages that you can use. One is in the stats program Stata. I really like Stata. I feel like it's really user-friendly. The downside is it costs money to use it or to buy it. You've got to purchase a license. But this is essentially you can like sort of download the Robu Meta package, and I have that in the resources list if you want to find the Robu Meta package. And then once you've loaded into Stata, it will be there all the time. And so basically this is the syntax that you would use to calculate the average weighted effect size. You basically, you have a study identification number, your variance, and then the weight type. Again, I said we wanted to use random weights or random effects model, and then the rho at 0.80. And so the rho is the assumed intercorrelation among the effect sizes. And one thing that I've found, and has been found in a lot of other studies, is if you change this assumed value of rho to like say 0.1 or 0.9 or 0.3, it really doesn't have any impact on the effects. But I usually do those kinds of sensitivity analyses to test that out. R is another package that has Robu Meta. The syntax is slightly different, and you have to find the Robu Meta library, and then basically you can read in your data. And then run your analysis based on your data. And so you can see that we're using effect size that's our variable name. So that's what we're running the meta-analysis on. And we've got study ID, variance, and then the rho again. And so basically these are two different packages that do the same thing. But R is free. This is what the output looks like when you run RVE in Stata. So this is the Stata results. Whoops. And you can see they've got level 1 and level 2 here. So level 1 is the number of effect sizes that you had in your meta-analysis. Level 2 is the number of studies that you have in your meta-analysis. You can see that the minimum number of effect sizes in a study was 1, and the maximum level was 40. So there was one study that had 40 effect sizes in it. The assumed rho is 0.80, as we mentioned. This is the average number of effect sizes here, and then the tau square is a measure of variance that I'll talk about in a minute. If you look at the coefficient, that is your average weighted effect size. So 0.57 is your average weighted effect, and then you've got your confidence interval that basically is around that effect size where we think the true effect lies. And the p-value and the confidence interval basically tell you the same thing here. One thing that's important to know, and this is not a problem with this study because we have 40 studies and 170 effect sizes, but you got to look at your degrees of freedom. When you use robust variance estimation, it's really not stable if the degrees of freedom are less than 4. And so if you have degrees of freedom less than 4, then you really shouldn't trust the results. And so that's just an important thing to remember. You can see that this is the results for the R package. They are the same, right? So we've got 40 studies, 170 outcomes. We've got our rho. This provides I-square. That's another measure of variance that is provided in R that's not provided in Stata, but our tau square is the same and our effect size estimate is the same. So these things really provide exactly the same results. And you can see there's a note in the bottom of R that if degrees of freedom are less than 4, do not trust the results. Stata will give you that warning as well, but only when the degrees of freedom actually fall below 4. This is just some code that you could use to, or some syntax that you can use to run a forest plot. And so I won't spend a lot of time on this. I do have it's in the slides, and then there's a resource at the end that sort of has all the syntax for these packages. This is what, again, this is the sort of the rest of that. Before I didn't show you the whole forest plot. This is sort of the rest of it, and you can see the bottom here. This is the effect size, and the range of the effect size is the range is really wide because of that. Those earlier studies that had really large standard errors, but essentially that's how you run the forest plot. So kind of a nice forest plot. I like that it provides different sizes for you. The other thing is you can modify this if you want to add things like confidence intervals and things like that. The other way that you could run the meta-analysis is with multi-level modeling rather than robust variance estimation. So for that you would use meta-4, which is a package in R. There's no Stata equivalent that I know of. But in the R package, you can get the R package for meta-4 here. It's also at the end. Here you've got to sort of load the library for meta-4, install the package club sandwich. But then essentially what you can do is this is the syntax to run the multi-level model. And this is what the results will look like for that. And so you can see here that that essentially, let's see. There's 169 degrees of freedom. That's because there's 170 effect sizes. I'm not sure where I'm seeing the. I guess I'm not seeing. I guess these are the effective effect sizes or something. Sorry, I'm not sure exactly why this isn't saying 170. But anyway, we get our effect size estimate down here at 0.54, and then our confidence interval around that effect size. And so meta-4 is another way to do this. Again, you only want to do this if you've got 50 studies or more. So then the next thing that we want to do is I mentioned that we have these sort of tests of heterogeneity. They give us this tau square statistic and I-square statistic. And so essentially, those are sort of that measure of heterogeneity. When we look at the average weighted effect in the forest plot, you can see that there's some variability. Now, this is such a small graph because it's -5 to +5 effect sizes. So these are really constricted. But if we had a bigger graph, you would see the variability around that. And so that's what this is measuring, is that heterogeneity. Let's see. Okay, so the I-square value that R gives you is the percent of variance the percent of the error that's due to between study variance. And so that's important to know, because if it's high, if it's say like 80% of the variance is between study variance, then that means that we can analyze that. One of the issues though around this is that the percent of, it could be that there's a really small amount of variance, and that there's 80% of it is between study variance, but there's really not a lot there. So we need to sort of look at some other statistics like the tau and tau squared, which gives the estimated variance of the true effect, and prediction intervals, which are based on tau. And essentially what those are is they provide an estimate of, if you're sort of thinking about the pool of potential studies that you could do, and you could pull effect sizes from where those effects, how big is the interval around which you could pull those effect sizes, so in a lot of studies. And so here we've got confidence intervals, fixed effects, and random effects. And you can see the confidence intervals around these effect sizes are sort of the width of this diamond, and the prediction interval is a lot bigger than that. And so essentially it's giving us sort of a sense of like how much variability there could potentially be in this distribution of effect sizes. One way to calculate the prediction interval is in Bornstein 2019. I've got a resource. I've got the resource for Bornstein 2019, or the reference for you. So he gives you the website that you can go to, or the exact web address that you can go to pull this. But essentially, it provides you with you plug in the statistics up top, and it provides you with the prediction interval around the effect. So when you're all said and done, you might have a table something like this, where I might have multiple analyses that I've run. I call this the field calls this a shifting units of analysis approach. So I might have my overall effect here, where I have all of the measures that I've looked at across all of these studies, and so this includes all writing measures. There are 73 studies, and there were 348 effect sizes. And you can see that the I-square is pretty high, so 87% of the variance is between study variance. And the tau square is pretty high, so it sort of suggests that there's quite a bit of variability in these studies. And then the prediction interval is pretty wide. So if I'm doing a study in the future, mostly it's going to be in this negative effect range, but there may be times where I do a study and I could find like a null effect or even a positive effect comparing kids with reading disability to their chronologically age-matched peers. But then I also have a shifting units of analysis approach. So rather than having all my measures, I wanted to sort of examine whether the effect was whether the effect was significant for handwriting measures only, or organization only, output only, that sort of thing. And so I can run each of these separately. You can see that I've got an I-square, a tau square, and then my prediction interval around each one of these, and then the confidence interval, which is where I think the true effect lies. After you've run your sort of overall analyses, then what you want to do is then sort of run a moderator analysis to see, can I explain some of this heterogeneity in here? Can I see whether or not there's some variables related to this study or related to what's going on that might explain some of that variance, right? So what you should do is always have predefined moderators, things that you know that you're interested in. So if you're looking at an intervention, and you know that like when technology is used with this intervention, that usually the effect size is larger, and you want to sort of test that. Well, then you've got some theoretical rationale for that, and so you want to have these moderators predefined. If you do some post hoc analyses, and this happens, and there may be reason to do it from time to time, but you want to sort of say that these are exploratory analyses and be really clear about that. And then you want to also be clear about whether moderators were analyzed separately, individually, so you ran a model with individual moderators, or if you include them all together in a meta-regression, is what we call it. Here's an example of sort of between or within study moderators. So I've got a group of studies here. I've got effect sizes 1 through 3 in study 100 and 1 through 3 in study 200. And you can see that whether or not people binge is really associated with the study. So this would be a study level moderator. There's no variability in this moderator within the study. But then age varies within the study and across studies, right? And so this would be a moderator variable that you could look at between and within. And so you basically analyze them the same way, but it's just good to be clear about what exactly you're looking at. When we do a meta-regression, basically it's the same as a regression model. So if you're familiar with the regression models, then essentially you run it the same way. The number of moderators that you can include in your regression is based on the number of studies that you have included, not the number of effect sizes. The rule of thumb is that you can include one moderator for about every 8 studies. And really, I've been finding that it's more like 10 or 12 studies It really depends on your corpus of studies. Again, you've got to look at those degrees of freedom. So if you end up with less than 4 degrees of freedom for any one of your moderator variables or your coefficient, then the results are untrustworthy and you can't run that. And so the models will tell you that what the degrees of freedom are. You want to try avoiding analyzing highly correlated models or moderators together. This is what a moderator analysis would look like in Stata. I've got the, sort of the syntax up here. You can see that I've got effect size, but then I've got my several moderators that follow the effect size. And then I have, again, my study ID that I'm doing random effects. I'm using var as my variance component in my row. And you can see a lot of this stuff is the same. The tau square is 0.145 still. And you can just kind of look at your moderators. Now, what I've done is I have C quality, which means that I centered the quality variable. And then the rest of these are essentially dummy coded variables. So the grade EL is grade level elementary school or upper grades. Signal words, or whether the study included signal words in the instruction or did not include signal words. Writing is, again, included writing or did not, 0 and 1. And then the number of text structures taught. They're up to 5 text structures, and so it's like 1 through 5. As you can see, you can look at your coefficients here, your average weighted effect here, 0.418. This represents, and this is what we do, sort of like what Mark and I call plug and chug. This represents just this alone. If all of these, the rest of these are zeros, then it's a study with average quality, with a student at the elementary level, because elementary is 0 and upper grade's 1, that did not use signal words, did not include writing, and it only included a single text structure. And so that's what the effect would be. So the rest of these would be 0. And then if I want to sort of examine, then I would sort of like plug in, what if I have my constant 0.418, and then I want to see, what if they added writing? So then I'm going to multiply the coefficient here by 1, and then I would add these two things together. So you can see that adding writing, sort of a pretty large difference in the effect. You go from like a negative 0.41 to essentially 0. So there's sort of an effect for writing here, although we had a negative constant. I don't remember. There may be a mistake in this, but you get the point from this essentially. And then what you can do is we can look over at our confidence intervals and our p-value, and we can see that we do have a couple of significant moderators. The number of text structures taught. So as teachers teach more text structures, then for every text structure they add, you increase the coefficient or increase the effect. And for teaching writing, you also increase the effect. And you can see the confidence intervals around those. The rest of the moderators were not significant, and so that tells us that. Let's see, how am I doing on time? It's about 11:15. So I'm going to just take another minute. I'll take the extra 2 minutes to 11:15, and I'll just briefly kind of cover some of these other things. Things to think about are publication bias. There are some different analyses you can do with publication bias to see whether or not published studies that you have are if you have small study effects, if maybe they're only there if you only have small studies if the effect is large, but not if the effect is small or null. And so you can see this sort of like empty area down in the left-hand quadrant of the graph. You can do trim and fill analyses where it will trim the effect sizes and then fill them. So these are just things so and then you can also do things like PET and PEAS tests. So there's several different ways to examine publication bias analyses. It's important then to sort of, when you have your effect size, to think about, first of all, what is the model telling you, right? And then is it meaningful? Can you translate the effect size into something meaningful? I've given you a resource here, so translating the statistical representation of effects of educational interventions into more readily interpretable form. So you have an effect size. What does it mean? Beyond just is it small, medium, or large? what does that mean on a test? Like, so for example, does it mean they get one more question right? Does it mean they go from having a B to having an A in the class? What exactly does that effect size represent in real terms, right? So you want to really just be careful in your thinking about, what your results are. There are limitations to meta-analyses. If you don't do a strong literature review, then, you're going to be dead in the water. You're going to have to probably do your literature review over again. If you combine studies with intervention outcomes that are not theoretically similar, right? So if you, for example, we've been hearing a lot about these two drugs for coronavirus, hydrochloroquine and remdesivir. And if you were to sort of include both of those in a meta-analysis and you found that, oh yeah, they're effective, well, what is that really telling you? Are they both effective? Is one effective and one's not, and one's driving the analysis and one's not? So that would be a really sort of a bad meta-analysis to do. So you want to really make sure that you're thinking about your interventions and the outcomes. So if we were looking for outcomes and we're like, oh, well, this intervention was effective for both reading and math interventions, well, why would that be the case? Or maybe if we find no effect, it's because it was effective for reading, but it wasn't for math. And so then we end up with this like sort of weird effect size that's not significant. So you really want to be careful about sort of your thinking and how you put things together. I apologize that I'm sort of running out of time. I'm not going to be able to talk about meta-SEM very much, but just basically, if you want to run a meta-SEM, essentially this is correlational. You'll be using correlations as effect sizes. And you can look at really simple models, structural equation models, and you can estimate path models based on correlations that you find. If you can do two-stage meta, essentially what you're going to do is you create correlation matrices for each study, and you can see that up top. And then you sort of estimate those correlations, and then that will, once you have sort of a pooled correlation matrix, it can then help you estimate the path model. There is a one-stage meta-SEM as well, where you go directly from the correlation matrices into the structural equation model. You can have missing effects in here. So if you had like study 1, you can see that study 1 has more effect sizes or more correlations than study 3 on this graph. And so, if you're ever interested in doing meta-SEM, I'm doing one with a couple of colleagues, Mark and a couple of other people, and so we're looking at a couple of things, doing one for the first time. So if you have questions, we're figuring it out. We have some colleagues that know how to do this. There are really cool ways to sort of analyze moderators and stuff like that. So just so you know that that's a possibility at this point. At the end of this here, I've got some resources for you for R packages, Stata, Campbell collaboration calculators that I shared. The handbook on research synthesis and meta-analysis is outstanding. It really has all the up-to-date methods, so you can use that. And then some of my references that I talked about today. So I guess that's it. I want to leave some time for questions. Sorry, there's only about 12 minutes, but it's enough time for some questions, I guess, right? I don't know how to do. I think the way that we're going to do questions is if you click on participants in your Zoom, and it should open a window where you can click raise hand, and I can see if you're raising your hand, and then I think I can have you. Oh, thank you, Monica. Appreciate it. Hopefully it wasn't too fast. I know it was a lot of information all at once.
Michael?
Yeah.
I couldn't find the raise hand, but I have a question. Can I just?
Sure. Yeah, absolutely. This works too.
Thank you. I tried and I couldn't see the raise hand thing.
All right.
I've kind of been very attracted to meta-analysis for the same reasons that you started the presentation out in terms of seeing the forest through the trees. But heard some criticisms of meta-analysis in the idea that if you're taking a bunch of studies that are poorly done and you're combining them, it's just going to be, yeah, exactly, more junk. But you talk about in here measuring the quality of a study. So what are you using to measure that quality?
Sure. So, and I can share some resources after this as well. Maybe I can add them to the presentation, the PowerPoint, so that they'll be posted for you. But essentially, there are lots of different quality indicators, papers. There's, Campbell Collaboration has some, Council for Exceptional Children has some, and so they may, there are like different quality indicators that you might think about. So one is randomization. So does the study include randomization or not, right? Every study's different, so there are other things that you'll think about, but could be whether or not there's attrition. If the attrition rate is really high, especially if it's differential, right? So attrition is really high in the control group, but not in the treatment group, and maybe the control group might have been different, or you're looking at different populations there, right? Or could be something like when I'm doing intervention research, if we have one interventionist or one teacher in the treatment group, and then one teacher in the control group, or one teacher that teaches several treatment groups, but they're the only teacher, then it could be that the impacts of the teacher themselves could be really a great teacher and could be really motivating to the kids, and they may find effects that or they may get kids to do things that. And they may not even know the ways that they're sort of altering the intervention, right? So having multiple interventionists in each group. So those are kind of some of the things. And you might look at sort of whether they're ceiling effects or floor effects on outcome measures, because that would truncate your effect or that sort of thing. It could also be that you don't have very reliable measures, and so looking at the reliability or whether those things are reported in the report. So there's a lot of those kinds of things that you might look at. So sometimes people will put quality together. They'll sort of give points for each of these things, and then they'll give like a proportion of the quality indicators met, and they'll analyze whether or not that's a predictor of the effect. Another thing that you could do is if you had really low quality studies, you could you could run the meta-analysis with those studies in the meta-analysis and then take them out and run it again and see if the effect size is very different, and if it is, then you might say, okay, well, there's something here that's really sort of systematically problematic, right? And so you can kind of look at it that way. So I don't know if that answers your question.
It does. Thank you very much. Thank you.
See, it looks like there's some people in the chat. Oh yeah, Mark was just mentioning that NIH has some study quality assessment tools as well, and he put the link up there. Thanks, Mark. We used some of these in our class, but off the top of my head, I'm not like answering some of those. But that's a great resource. So if you want to look at the NIH quality indicators, those are great as well. Other questions? You can feel free to jump in and ask if you can't find the hand raise button.
I have a question.
Sure.
Thank you very much for the presentation. It was very, very insightful. I've started kind of looking into IPD meta-analyses recently and like just kind of reading up on the literature. And I've noticed that there's also a 1 and a 2 stage approach. And I'm wondering what the differences are between the meta-SEM 1 to 2 stage approach versus the IPD, if there are any similarities or overlap between those.
Yeah, I'm not sure what IPD is. That's not something I'm familiar with. Can you elaborate a little bit?
It's the individual participant data. So essentially you have you have the raw data essentially, and you're working based off of that.
Sure. So there, I think you have a lot more possibilities. You can really calculate the effect size yourself. The issue with those sorts of studies is that not a lot of studies give you participant level data for all of the participants, right? I have found some dissertations that do, but rarely do I find a published manuscript that has the data. But more and more, I think now with people sort of pre-registering their studies and putting their data out there, I think that you'll see these meta-analyses come up a lot more. But I'm not really as familiar with it because I don't, or the two-stage approach with that, because I don't, I haven't done I haven't done any of those because I really haven't been able to get my hands on that information.
Okay. Thank
Sorry,
you.
I wish I had.
No, that's fine. Because I've actually thought about also, well, what happens if like we were to do a meta-SEM approach to it too? And if that would be comparable, or maybe not comparable, but if that would still be as effective, and take.
Oh, I'm sure. Yeah, if you could calculate correlations, then you can absolutely do that with meta-SEM. I don't see there being any problem with that.
Okay. Thank you.
Sure. Other questions? I really appreciate the questions that you guys have had. These are that last one was tough. It's like something I'd never heard of before. I always worry about that when I'm doing presentations, that I'm like, somebody's going to stump me, and then totally it always happens. So it's like, that's why I worry about it, because it always happens. I always get stumped. But I guess it's one of these things where this is a really big area, and I'm not a methodologist, but I do a lot of meta-analyses, so it's but I can't just be up on everything, and so I guess I got to give myself a break. But it's always tough to get those questions, but it's good. I'm glad they're really good questions for stimulating conversation and stimulating your thinking. Well, I guess if nobody has any additional questions, Seth, do you want to sort of end the... Oh, it looks like there might be another message. Oh, thanks.
I have one question.
Oh, sure, great.
This is Monica. Regarding the comprehensive lit review, yeah. I really wrestle with this, like how, with the internet and all the resources we have, when do you stop? I mean, how far?
Yeah, I had that bullet point in there. When do you stop? And I didn't cover that really. I think that you stop. So you want to make sure that your original review is comprehensive, and you want to make sure that you're looking for dissertations and that you've got like really good search terms. And so you've done those things. You want to do the forward search and backward search of probably every study that you include in your meta. You don't have to do them for any of the studies that sort of don't meet your criteria, but any that do, you probably want to do that forward search and backward search. And then contacting authors, you can't contact every author, right? And so I think that you sort of like choose a handful of authors that you think are really, really know the space well, might have students that have done similar studies that didn't get published, maybe a master's thesis or something like that. And then at that point, I think you can stop. If you've contacted a few authors and then you've done the forward and backward searching, I think that but you really do need to look through the dissertation. So the challenging part of the dissertation search is that if you've ever run a search in ProQuest, you can get tens of thousands of results, and it will take you, it will take you months to go through all of those. So what we often will do is really try to tighten up our search terms, make sure that, if we have terms in there that could be, confused with something else, like, for example, we have a student now who's doing meta-analysis on students with visual impairments, and so they put blind as one of the search terms, but they have to say like not double blind, right? Because then you get a lot of things that are just basically research oriented, but not about kids with visual impairments at all. And so, so you got to be really careful with your search terms. And then what we will do is we'll often say, what can we look for that's in the title and the abstract? Because if you look through if you open up your search terms to every term in the document, then that's where you get the tens of thousands. And so if you can really can restrict those terms to something more manageable, and that's that sort of upfront work. So you want to kind of like run these searches once or twice, and then try to refine your search terms. You don't have to just run it once and say, okay, well that's it. I've run it, so I have to look through all of these. I mean, you can really sort of take the time to make sure that you're getting a reasonable number of studies. And so that's probably where you'll spend the most time.
Thank you.
Sure, absolutely.
Hi, Mike. This is Bing. I'm from Food Science, and thank you very much for the presentation. Since you mentioned about the dissertation, I think it's very good to include the dissertation trying to reduce the publication bias. And on the other hand, there could be an issue that the dissertation study could be the same study that later is being published. So usually how do you do the comparison to make sure you don't really double dip the same set of data?
Yeah, you have to be very careful about that. And sorry, I'm like, my screen went dark for a second. You have to be really careful. When you have studies that have multiple authors, one of the things you do is you look at the participants, you look at the methods, you look at the length of treatment, if it's a treatment study. You really try to look at the samples, any of the data that they share. And if you see that these things are the same, then you want to make sure that you're not including that study twice. Sometimes, often the dissertation will be more than the published paper, and maybe you can even extract a few additional effect sizes out of that, and that's okay. So what you would want to do is when you let me see if I can find my screen sheet, share my screen really quick here with you. So you can have multiple reports. So if you had like Abu Rabia 2004, and then you found like Abu Rabia 2001, and it was but you keep them is the same study ID. And you want to make sure that if you have multiple effect sizes that you're not, duplicating effect sizes. But if there's additional information in one report, then you can add that information in. Because really, the thing that you're analyzing is the study itself, not the report, right? We want to make sure that we're capturing all the information from that study. And so if you find additional information about it, then it's okay to include that. In fact, I encourage people to do that. But you're right, it's just something that you need to be careful of. And so whenever you have dissertations, one of the best things to do is just cross-reference the authors.
Okay, thank you.
Sure.